you could spend some time with me today. So to begin with, this is an RCEP compliant webinar. That means that we can give you continuing education credits, and I'll remind you about how to do that at the very end. We don't say here how many hours this would be. It will normally we try to keep these to an hour, but I know I have more than an hour's worth of material today. So it's probably going to take about an hour and a half. If you need to bail out, then bail out. If you stick with it through the end, though, we'll get you an hour and a half worth of credit. So the course description, we're going to talk about the design elements of all dielectric self-supporting cable, commonly known as ADSS. We're going to talk about how the tubes and core should be made and why that is important to the cable's long-term performance. And we're going to touch just briefly on sag and tension considerations for ADSS and how you know when you need a track-resistant jacket. As I say, a lot of material, so we're going to hit it hard. So here's some specific learning objectives. I want you to understand each of the 8 design elements. I want you to understand important parameters of how to make the tubes and the optical core itself. I want you to understand how you can get the sag and tension data that you need. And we want you to understand rough idea, when you need to use a track-resistant jacket. So our format, we've already done the introduction and the course description, learning objectives. Now we're going to hit the presentation. And like I say, I'm sorry it's going to go long. If you need to drop off, do what you need to do. We will have questions at the end. We ask that the questions be related to today's topic, which is the ADSS fundamental design characteristics and engineering. Let's get started. So first, we actually need to back up a little bit and take a look at 2 basics that apply to optical fiber and loose tubes, because these things apply to ADSS, OPGW, and other types of fiber optic cable, but they're important, and we'll see why as we go through this webinar today. So first up on the fiber, the overwhelming majority of fiber that we here at INCAB use and that we see in the American marketplace is low water peak single mode fiber. The international standard for that is ITU-T G652 Table D, so it's a specific entry within that standard. And an example of this fiber is the Corning SMF28 family of fibers. An important thing about this particular type of fiber is that fiber from different manufacturers, world-class manufacturers, I will say, are generally splice compatible. So you can take Corning's SMF28 Ultra, which is their latest version of their SMF family of low water peak single mode fiber. You can take the Corning Ultra product and splice it to OFS all wave fiber, and they will work fine. As a general rule, you can go about 60 to 90 miles before you need to regenerate a signal with this type of fiber. For now, you just need to be aware that there is other fiber types that are available. Non-zero dispersion shifted fiber is one of them. Not going to talk about it today because of time. And multimode fiber comes up. Multimode fiber, in particular 50 micron, comes up with some sensing applications. But you don't today see a lot of that with ADSS, other types of cable. So again, overwhelmingly, 99% of the fiber that we process is single mode fiber. Within that fiber, there are different characteristics of the fiber, but the single most important characteristic of the fiber is its attenuation. And attenuation is loss of power over distance. That loss is expressed as dB, decibels, a unit of loss. And then, so decibels per unit of length. The most common that we see is dB per kilometer. But the unit of length could be something else. Here in the United States, you will see dB per mile, and you can see dB per 1,000 feet. In theory, it could be dB per whatever, qubits, furlongs, whatever. It's just loss per unit length. And what that means is you have a certain amount of power that you inject in the cable at its beginning, and then over some distance, you get less power out. And that loss is the attenuation. Chromatic dispersion is another important characteristic of fiber over long distances. But again, because of the interest of time, we're not going to talk about that today. So we talked about the fiber. Next up, loose tubes. So today, around the world for aerial cables, loose tube construction is what you see in 99.99% of cable. And in fact, in my considered opinion, it's the only type of construction that you should see in aerial cables. The aerial cable environment is demanding, temperature is changing, and so that will change cable elongation, not so much with ADSS, but some. And you also have continuously changing environmental conditions. So wind and ice loading, the wind is changing throughout the day. Parts of the world, ice can change, maybe not necessarily every day, but certainly throughout the year, you get changes in that. So you get changes in loading on the cable. And because ADSS is dielectric and made out of materials that are rather elastic, its length will change. So it's constantly moving and constantly changing. And the loose tube construction is conducive to facilitating the fiber being protected from those changes. Why does it protect them? Well, because it allows the fibers to move in response to changes in elongation of the cable or the tubes themselves. The basic concept of how this works is that you lay the fibers in the tube in a sinusoidal shape. And so over a unit length of tube, you have slightly more fibers than you have tube length. Typically, you're going to see around 0.25%. Could be a little more, could be a little less. It shouldn't be much less, though. And so what happens is when this tube elongates because of tension or whatever, but in ADSS, it's 100% really tension. The fibers just begin to straighten out. And that ratio changes until it gets to 1. And when it gets to 1, that means that the fibers are picking up whatever tension is on the tube that is causing the tube to elongate. And so that's when we say the fibers are now under strain. So this extra fiber per unit length of tube or cable, so you can use the term for both, is called excess fiber length. In general, higher is better. Why? Because the higher the EFL is, the more range you're going to be able to protect the fibers from tension. Now, fibers are glass, but glass by its nature is brittle. So you can understand that cyclic loading on the fiber itself, which is what you can expect in an aerial cable environment, on a brittle material, nothing good can happen. So to the extent that and bad things can happen, specifically the fiber can develop cracks, and then the cracks can propagate over time, and then the fiber can ultimately just break. And that's bad, obviously. Nothing good can happen, bad things can happen, so you try to protect the fibers from the strain. And we're going to see how you do that as we go through this presentation. The zero fiber strain margin is specifically that point where the fibers begin to experience strain. And usually we talk about zero fiber strain margin for the cable as a whole. We don't just talk about it with the tube only, generally for the cable as a whole. And we'll see this later. So those were our basics. But a couple more points on the loose tube itself. You can understand that in order to get this sinusoidal shape, I have to have the space to do that. So there is a limit to the number of fibers that I can put into a tube and still get good sinusoidal shape. If I exceed that, I've overfilled the tube, and that's not good. If I put too many fibers in there, the fibers lose the ability to have that sinusoidal shape and move freely. Not good. The other thing that's a practical matter today is that in today's world, fiber counts have gone up, and you're regularly seeing more than 12 fibers per tube. Why is 12 fibers per tube important? Well, it's important because traditionally, the fiber color coding system that we use maxed out at 12 fibers. So what do you do beyond that? Well, there are a couple things you can do. You can either use bundling or binder threads, where you take 12 fibers using those 12 standard colors, and you wrap a binder thread or a bundling thread, just different terminology for the same thing. You wrap them around that group of 12 fibers, and you color code that thread. That's one way of distinguishing one group of 12 fibers from another group of 12 fibers. The other technique that you could do is use your 12 fibers, repeat the 12 colors, and add a black ring mark to each of the fibers. And that's known as ring or band marking. Again, different terms, same concept. Both are used today, but in general, with ADSS, the bundling or binder threads are what's more common. And it works because if you go back and look at your loose tube, the way it's drawn in this picture here, you see each of the fibers has the same amount of excess fiber length to them, and they're in phase with one another. 30 years ago, that wasn't always the case. One fiber might look like what you see in the picture, and another fiber might be out of phase, or it might have a slightly longer period to it. You had more what I term loosey-goosey loose tube. But today, each and every fiber is consistent and in phase. And so that means that if you're using bundling or binder threads, it works well because you end up with the entire bundle moving as a unit if it's been wrapped with a bundling thread or a binder thread. Works well. So ADSS cable itself, just to remind everybody of very basics here, all dielectric, self-supporting. So the dielectric means no metal components, and that's important. So if I add any metal into the cable, it is now no longer all dielectric. It is something different. And self-supporting is important because the cable is designed to support its own weight. So it hangs from the structures and it's supporting itself. It's important. As a practical matter, what this also means is that ADSS can be used underground as duct cable. It's not going to hurt anything. You could lash it too, for that matter. But the opposite is not true. So you can't use duct cable as ADSS because it's not designed to support its own weight. I mean, maybe you could if the spans are incredibly short, but as a general rule, that's true. And likewise, cables that you might lash on an aerial system, they are not ADSS because they're not supporting their own weight. And armored cables, for example, are not designed to support their own weight. So they are not ADSS. All dielectric and self-supporting is the definition of an ADSS. The governing standard for it in the United States is IEEE 1222, and internationally, it's the IEC 60794-4-20. Here in the United States, we often see people talk about ADSS as short span ADSS and medium span ADSS and long span medium ADSS. Those are very vague terms, but we'll try to give some context for that as we go through this presentation. So now we're up to our design considerations. And you'll recall that I said there are 8. They are jacket configuration, jacket material, strength material, the core design, the tube design, the number of fibers per tube, what you make the tube out of, and do you have adhesion between the outer jacket and the strength element? I know this seems like a lot. By the way, I see somebody raising their hand. Please hold questions for the end. I'll get you at the very end. So it's a lot, but we're going to break it down, and it will be you'll get it right away. So first up, jacket configuration. You've got two options: double jacket and single jacket. We'll talk about double jacket first. It's the traditional design of when ADSS was first introduced. Advantages: highest reliability. It consists of a cable core. So you take those tubes we talked about with the fibers in them, you strand them around something, and then you put a jacket over that. And then over that, you put your strength element. And over that, you put an outer jacket. So exactly what you see here. That inner jacket is protecting your optical core here. This construction allows you to go the longest spans over 1,600 feet, or about 550 meters is possible. But the disadvantages, it is more expensive to do this because you've got more material. Roughly, very rough rule of thumb would be 5 to 25%, depending upon the fiber count. You're also increasing the diameter and weight of the cable. That's part of the reason you have more costs there. And by increasing diameter and weight, you may be increasing dead end cost, you're increasing structure loading, and so forth and so on. So there can be kind of a ripple effect from this. In contrast to the double jacket, you have the single jacket where you eliminate the inner jacket. So you take your cable core and you apply your strength material directly over it, and then you put an outer jacket on over that. So advantages: you've reduced the diameter and weight by doing this, and you've reduced the cable cost. But the disadvantages, or the cost of doing that, is you've lowered reliability and you've reduced the maximum span length or loading conditions that the cable is capable of supporting. So I say here, this is a rough guideline, less than 650 feet, around 200 meters. And loading conditions, we'll come back to that in just one moment. And that moment is here. So what should you use, double or single? Well, if any of the following applies, we recommend that you use double jacket construction. So if the spans are more than 600 feet, if you're using NESC heavy or similar conditions, because I know I've got international customers here, well, what do I mean? Well, NESC heavy means you've got a significant amount of ice coupled with wind loading. Another significant, and it's admittedly a vague term, would be high wind loading conditions. It's kind of a judgment call as to what the exact demarcation point would be. But basically, high wind and or high ice loading, I think you should stick with the double jacket construction. If your fiber count is above 144, then I think double jacket construction is most appropriate. And then if highest reliability is what you're going for, then that too means use the double jacket construction. If you're putting cable up and it absolutely needs to perform for 20 to 25 years, your best bet is the double jacket construction. Single jacket is appropriate if all of the following apply. So here you only need one to throw you into the double jacket category. Here you need all of them to stay within the single jacket category. So the spans need to be below 600 feet or about 180 meters, roughly. Light or medium loading conditions, by which I mean not a lot of wind or ice. Very vague term, I understand, but hopefully you understand the concept. And if the fiber count is less than or equal to 140, for single jacket construction can be fine, and when good reliability is good enough. So you've got an alternate communications path, or for whatever reason, it's not critical that if the cable were to fail. Good reliability, good enough. So the best choice depends upon how you balance these variables for your specific project. Next up, jacket material. You've got three choices for jacket material. You've got high density polyethylene, you've got medium density polyethylene, and you've got low density polyethylene. So let's go back. We'll look at high density polyethylene first. Its advantage is that it is tough and durable. But like everything, it does have some disadvantages. It makes the cable more expensive. It makes splice prep harder. And this material is susceptible to cracking in very cold climates. So you have to be kind of careful if you use it in such an environment. Next up, medium density, still tough and durable, but its disadvantages is it's not as tough and durable as high density polyethylene, but it does better facilitate splice prep, and you do save a little bit of money using it. And then our third choice is the low density polyethylene. And in our opinion, it should only be used for that inner jacket. It should never be used as an outer jacket, whether it's ADSS or duct cable or armored cable or any other cable, in my opinion. It should only be used for an inner jacket, in my opinion. And so that's what we say here. I think that medium density gives you the best balance, so the best overall choice for most applications. There are some times when high density polyethylene is appropriate, and especially if tracking resistant comes up. Most tracking resistant jackets are actually HDPE with an additive in it to give you the track resistant. And then, as I've already said, low density should really only be used for the inner jacket. It does help make splice prep a little bit easier. Next up, strength material. You got another three choices here too. First up is aramid. It's commonly known as Kevlar, but Kevlar is really the trade name of DuPont, who invented it. Aramid is the more generic term. It's the original strength material used with ADSS, and it's still by far the most common. Like 99% of the cables we make use aramid, but there are some other options, and you'll understand why they're there in just a moment. Great advantages, very high strength to weight ratio, excellent thermal stability. And because of these two properties, you're able to limit the fiber strain at your maximum rated design tension. Maximum rated design tension is the terminology used in the IEEE standard. Here in the United States, you will also see the term maximum rated cable load. They mean the same thing. This is just an older term that, for whatever reason, the IEEE did not adopt. So what you want is, as the name here, maximum rated design tension implies, this is the maximum tension that the cable should experience under any and all loading conditions. So however much ice and wind you want to throw at the cable for design purposes, you want to keep the tension below whatever this cable is specified at, whatever its MRDT or MRCL is. You got to keep it below that. And with aramid, you can make sure that you don't have fiber strain at that point, or that you've at least minimized it. You can keep it below 0.2%. Ideally, you want it to be zero, and we'll talk about that more later. But at least you can keep it to 0.2%, which is considered the best maximum limit if you're going to allow strain. The disadvantages of aramid are that it's more expensive than the next option we're going to talk about. And there are times when it can become conductive. You have to have a jacket breach, which allows water into the cable, plus you're in a high electric field. So you've got some bad things already going on. This can make it a little bit worse. Yeah, I'll just leave it at that. Next up is fiberglass yarn. It is significantly more expensive than aramid. Its one really most important advantage, though, is the fact that rodents don't like to chew on it, and that includes squirrels. So if you use fiberglass in your cable, whether it's duct cable or ADSS, you get some rodent resistant. If you're grading it on the American ABC scale, you get about a C, because the little critters have already chewed through the jacket. it is going to give them some resistance, but I can only give it about a C. It helps. But significant disadvantages, it's lower strength and thermal stability when compared to aramid. So you have to use more to get a given strength. And because you're using more, you're taking more space, which means you're driving up the overall cable diameter about 10 to 20%. It's cheap though, so you don't actually increase the cable cost. In fact, you've probably dropped the cable cost. However, again, because of its mechanical properties, you're usually going to end up with higher fiber strain at that MRDT point, around 0.3 to 0.4%. So you got to balance things if you're using this material. Next up is FRP rod. So you can actually use the FRP that you use as the center element for strength on a cable. And this will absolutely stop squirrels and rodents. You can get an A, again, on that American grading system. You also get very high crush resistant. You end up with a cable that's very versatile. It could be direct buried. At one point in my career, I hoped it would prove that this design would be shotgun resistant. Alas, we did testing. It was not. So we're still on a quest for shotgun resistant cable. But it is very effective with the rodents. Disadvantages, though, it does cost more. It's going to have a much larger cable diameter and weight because you have to have the inner jacket. So that's already driving up your diameter and weight and cost in order to be able to strand these rods around the cable core. It's going to decrease your maximum spans, but you know, if you work at it, you can still get pretty long on this cable type. Your splice preps might complain about removing the rods. Not really a big deal, but it's not something they're used to, so you can expect some static about it. And then to give context for why you would consider the fiberglass or the fiberglass rods, the UTC, the Utility Technology Conference, did a survey in 2017, and the number one field problem with ADSS, the number one thing that was damaging cables in the field was shotgun damage. Hence my desire for a shotgun resistant ADSS cable. It's kind of the holy grail of ADSS cable design at this point. But a close number two was rodent damage, in particular squirrels. And so here's some pictures of what you see in the field. This, I actually think, the middle one, I think, is actually shotgun damage, but it was interesting to show that. But, you know, notice our little fellow here, what the heck he's trying to do. I have no idea, but they do significant damage to ADSS cable in certain parts of the world. So bottom line, what strength material do you use? Well, aramid is your go-to solution most of the time. The other two are special. You know, if you're having problems with rodents, you ought to consider them. So fiberglass yarn, if rodents are kind of a nuisance problem, you can put a rodent deterrent additive in the jacket, and you can get kind of a B rating there. If spans are short to medium and you're trying to cut costs, fiberglass might be a good option, especially in a fiber to the home project. FRP rod is good to use when you've absolutely got a big problem with rodents and you need to fix it. And you can get an A in rodent resistance. And then FRP rod, you do see used in fiber to the home drop cables, the flat type ones. So again, the optimal choice for this, which material to use, ultimately is about your project details, what you're trying to accomplish. Next up, core design. So when we've taken the tubes and talked about how you strand them around a center element, you end up with these gaps. And so what do you do with these gaps? Well, we don't want to just ignore them because we're engineers. We don't like to ignore things. So we end up with a choice of either we fill them, which is called flooding them, or a wet core, or we'll see in a minute, we can do something different. oh, actually, we see right now, we can use water-soluble yarns as another way of kind of what happens if water gets in. You just don't want water to be floating around in these voids. You need to do something to prevent it. So the water-soluble yarns use super-absorbing polymer. And that's a newer design concept compared to the flooded core that we'll see in a minute. It does make splice prep significantly less messy. It does lower weight a little bit, but it borders on being trivial. But the big disadvantage is that water does get inside the cable. So the water actually gets inside to the core before the water absorbing yarns can act upon it. In contrast, if you flood the core with a gel, oops, sorry about that. The gel keeps water 100% out, so it doesn't even penetrate into the core. That's a big advantage in my opinion. The gel is actually slightly cheaper. You see here 5 to 10%, but it does make splice prep significantly messy because typically when you're doing splice prep, you're removing about 2 meters, 6 feet-ish or so of the outer jacket or jackets. And that's a lot of gel floating around. And it really does make the splice prep messy. You'll see later, I'm not always sympathetic to splice prep people, but this is one instance where I am sympathetic to them. Again, or as I say, the gel was the original design, but in the United States, today you see only the dry core. Internationally, probably you see more flooded core. Which to use? In the US, it's got to be dry core. It just won't otherwise be accepted. But outside the US, the flooded cores are still used, and technically it's better. I have to say that. But as I say, US splice techs absolutely hate it, and I do have some sympathy for them on this particular point. The tube designs, you have the same problem. What do you fill the tubes with? Because of the concern about what if a tube gets breached and water gets inside? Well, you have the same solution. You can either flood the core or you can use water absorbing yarns. Super absorbing powder is also sometimes used, but that's considered an older technology. These days, you typically see either the traditional flooded core or the water soluble yarns being used. That's a newer design concept, but it's still been around 10 to 15 years, so it has a significant proven track record. The arguments for using dry tubes are, again, less messy splice prep. However, I argue against this because it's not a lot of gel when you're actually working with the tube only. And some splice preps have said that there's super absorbent polymer residue that comes off the yarn and gets on the fibers, and that they still have to clean that off before doing splicing. So this point is debatable. And people will also say that it lowers unit weight again, just like they did with the core. But in this case, I absolutely argue that the weight savings are trivial. The disadvantage here, and in contrast to the core, it has significant disadvantages, I think, of using a dry tube versus a dry core. As with the core, water gets inside the tube before it gets absorbed, so I don't like that. But more importantly, the yarn does nothing to help the fibers keep their sinusoidal shape. And that gel in the tube, we talked about the loose tube concept. As the tube elongates, the fibers flatten. The gel actually facilitates that. And when the tube contracts again, the gel is facilitating the fibers moving back to their original place. If you have nothing in there, there's nothing to help the fibers move in unison with what's going on with the tube. And what you've effectively experienced in the cable is that the fibers over time will tend to flatten in the middle of spans and bunch up the ends. And what happens then is they tend to push out from the ends into your splice enclosures. And to add insult to injury, in my opinion, you're also driving up the cost. So dry tubes cost more than flooded tubes, all else being equal. But I marked this as a controversial topic because, because other cable companies would strongly disagree with me on these points. Here's that migration and bundling illustrated. So when the cable is initially installed, you have uniform shape throughout. But over time, remember, in an aerial cable, it's constantly going to be moving, changing length because of changes in temperature and wind and ice loading. And what you're going to see over time is that the fiber is going to flatten at the middle of the spans and bunch up at the end, and then eventually it's going to push out of the splice enclosures. And here's a picture of that. It's commonly called pistoning. So the alternate was flooded tubes. This is the original design concept, and around the world still the most common. Its big advantage keeps the water 100% out, but more than that, it helps the fibers keep their shape. It helps the fibers move in unison, as I talked about, and so they resist that pistoning effect. It's actually increasing the crush performance, not just of the tubes, but also of the overall cable as well. And as an extra special bonus, it's less expensive. But the disadvantage are the perception that it's more messy during splice prep and that that's somehow going to add significant amount of time. But to give you context, when you're working only with the tubes, you're only stripping off 8 to 24 inches or so, 20 to 50 centimeters-ish needs to be prepped. So, and it's not a lot of gel, and it takes like 15 seconds. I have literally done time trials to confirm that. Cleaning the gel off the fibers, in my opinion, gives trivial time savings. And we're going to give context to that later. So what should you use? You can tell already, I think I've done a fair job of presenting the benefits of the dry tube versus the flooded tube. But I think you can tell already, I'm a fan of the traditional flooded tube design for aerial cables. A duct cable, dry tube's absolutely fine. You're going to lash a cable, no problem whatsoever. But for a true ADSS self-supporting cable, I absolutely believe that flooded tubes are the only thing that should be used. However, the reality is we're in a marketplace and you have to do what the customers want, and the customers, at least in the United States, want dry tubes. So we try to make the best dry tubes available in the world today, and we do use them, but we limit them when it comes to ADSS for short and medium span cables only. So how do I define that? I mentioned before, kind of a vague term, but I'll put some boundaries on it. Up to about 600 feet, you've seen that number before, NESC medium loading or equivalent. So a moderate amount of ice and wind only. And just to give you some boundaries of what I'm talking about as moderate, here's the NESC loading conditions. A quarter inch of ice, 6.5 millimeters, 4 pounds per square foot wind, or 190 pascals, and then this additional K factor, we call it. Long story about that. So we do make that sort of concession to what the market wants. Next up, how many fibers per tube? Well, traditionally, it was 12 fibers per tube, and it's been that way for decades. But as fiber counts have gone up in the ADSS world, 288 is a common cable fiber count. That requires, what is it? However many tubes, 24 tubes. So that's a lot of tubes. So, and that makes the cable big. So if you want to try to make the cable smaller, what you can do is go to 24 fibers per tube. But because this had been such an industry standard, everybody and everyone and everything is used to it. Your splice trays and whatnot coordinate well with 12 fibers. The lower fiber count does work well if you're making mid-span taps for like a fiber to the home architecture. Works a little bit better than 24, although 24 can work. But as I say, as your fiber count goes up, you're going to increase your diameter and weight. You're going to increase your cost from the cable, and it's going to take more time to do splice prep, right? Because more tubes to work with. Next up, the 24 fibers, newer, but again, you see a lot more of it because total fiber counts has increased. So I mentioned if you're doing a 288 fiber cable, if you're using 12 fiber tubes, you need 24 tubes. If you're using 24 fiber tubes, you only need 12. So that has the effect of decreasing cable diameter and weight. It makes the cable less expensive. It's reducing time for splice prep. 24 does work well with most trays, but you do need to check that if you're going to use the 24 fibers per tube, because there are some trays that are still in use that only need 12. It's not going to coordinate quite as well if you're making taps as 12 fibers per tube would. And as a consequence of that, it may not coordinate as well with some fiber to the home network architectures. Last up, there are other counts that are possible. A 48 fiber cable could be 4 by 12 or 2 by 24. If you're using 12 or 24, but you could also do these other counts. Okay, I think I'm back. Alexis, you lost me for a moment, right?
Yeah, I can hear you now.
Okay, good. So where I was talking about is with 48 fibers, you could do 6 tubes of 8 fibers or 8 tubes of 6 fibers. And in theory, you could do other counts as well. So less than 48 fibers, it actually turns out that 8 or 6 fibers per tube could actually reduce your cable diameter. And this would actually facilitate doing taps or mid-span access, which could be helpful for a fiber to the home type project. But the disadvantages of doing something alternate other than 12 or 24 is that it's not the norm. So that cable is not going to be in stock, which means somebody is going to have to go make it, which means more time, and it may increase the cable cost. And once you're above 48 fibers, you lose the benefit of this lower fiber count. It's going to increase overall cable diameter and weight and cost for that matter too. So, but you should know that it is available, and if you want it, it can be done. So what should you use? Well, your go-to solutions are the 12 or 24, and which you use is really up to you and how you balance the trade-offs here. The others might be appropriate if you're working on a fiber to the home project. You might want to consider it, but again, optimal choice is up to you. Tube material itself. So what do you actually make the tube out of? There are 2 materials that are commonly used today. First up is polybutylene terephthalate, which I'm sure I'm not pronouncing correctly, better known as PBT because you can pronounce it easier. PBT has high crush resistance. You get like more than 50% with PBT versus the other option we're going to talk about in a minute, which is polypropylene. It's a more durable material. Because of the higher crush resistance, it helps the cable work well with the dead ends. It's a self-supporting cable. So the tension in the cable has to transition to the dead ends, which are then connected to the structure. So this material helps that transition happen. It has excellent strength. It has excellent temperature performance. And when you cut into it during splice prep, you get clean cuts as opposed to ragged edges with the polypropylene. But PBT does have some disadvantages. It's stiffer, so that makes it more susceptible to being kinked during splice prep. And if you're doing mid-span access, there's a common tool today that's called a shaving type tool that works very well with polypropylene, but works very poorly with PBT. So you either need to use a slitting type tool as opposed to the shaving type tool, or you have to use a heat gun or both with it. So you have to be a little bit more savvy to work with PBT on midspan access than with polypropylene. And related to that being savvy, you also have to just be a little bit more careful because you don't want to kink the tube. PBT actually of the two materials is the more expensive of them as well. So that's another disadvantage of it. Polypropylene is very flexible, and so you're less likely to kink tubes during splice prep. And because of that, splice techs like it a lot. And that mid-span access, as I mentioned, you can do it with that shaving type tool. And it's cheaper, but it has significant disadvantages. Much lower crush resistance, as I said, on the order of half of what you can get from PBT, and the tensile strength is lower too. So it's not doing anything to help the cable work with the dead ends. It's not as durable, and it has much lower temperature resistance. So its properties will significantly change, and by change, I really mean degrade if your temperature gets below 0 or minus 20 Celsius. In my opinion, you should not use polypropylene tubes in parts of the country or parts of the world where the temperature can get below this limit here. And when you're splice prepping, it tends to more tear and leave jagged edges when it's being cut during splice prep. So I think that's not good. What do you use? Well, I think you can tell already. Again, I think I've given a fair shot at polypropylene, but I think the PBT is better. And we think it gives the best overall long-term performance for ADSS. ADSS. Duct cable, different story. Less concerned about duct cable. Armored cable that you're going to lash, also don't care. But for ADSS, which is today's topic, you really should be using PBT. But again, we have to deal with what the market wants. You know, customers always right, as the old saying goes. So we too are using polypropylene tubes for short and medium span ADSS. We plan to start doing that later this year. And again, up to about 600 feet, 180-ish meters under medium or similar loading conditions. So again, a controversial topic. Other suppliers would completely disagree with me on these points, I think. I think they might agree with my points, but still say that polypropylene is great. So there's that. Last topic. So as far as our design consideration, outer jacket adhesion. So in a coupled design versus a decoupled design, the outer jacket will have some adhesion, so some stickiness to the strength element below it. And that stickiness can range from light to heavy. And it doesn't matter what the strength material that you've chosen is, you're going to have adhesion. And the reason for this is that ensures that the tension that's in the strength material transitions smoothly through the jacket to the dead end. And that's going to help prevent jacket failures. And it may also permit the use of shorter dead ends. So it gives you a margin for error too with dead ends, all else being equal. But disadvantages are that it makes removing the outer jacket less easy, and splice techs will complain. You can mitigate this though by using 2 rip cords under the jacket. So if you have 2 rip cords, you can kind of split the jacket on both sides, sort of like how you peel a banana, and therefore remove it. And again, controversial topic, because other cable companies would say, no, you don't want to do this, but ask them to explain why you don't want to do this. And about the only thing they'll come up with is, well, it just makes it hard to remove the outer jacket. So in a decoupled design, you don't have any adhesion, and in fact, you might even apply a tape, specifically apply a tape over the core, specifically to prevent any adhesion. I say apply a tape over the core or the strength element, whatever it is. But in any event, if you do that, it's specifically to prevent there being any adhesion. That does make splice prep easier. But it disrupts the transition of the tension from the strength material through the jacket to the dead end. In turn, that can lead to stress concentrations, and stress concentration can lead to jacket failures. And then what's going to happen is the cable supplier is going to claim that it's the dead end's problem, and the dead end supplier is probably going to claim that it's the cable problem. And really, arguably, it's the accessory supplier is right, in my opinion. But the best thing that you can say about it is they don't work together as a system. And in an aerial cable system, you have to have the system work together. Just a fact. So you can mitigate that by using longer dead ends to some extent, but this is going to increase the cost, and the length is going to be longer, which in turn means that you may not be able to install the dead ends from the truck or from the pole rather, and means you have to have a bucket truck or some other way of installing them, driving up the installation cost is where I'm going with that. So here's some actual comparisons here, what you could get away with a coupled design for a certain maximum loaded tension, versus a decoupled design. So in a coupled design, you know, when the tension is not very high, you don't see a big difference here, but look at this one. The tension, 35 kilonewtons or 7,500 pounds. I only need a 67-inch or 1,700 millimeter long dead end. But in a decoupled design, I need 104 inches or 2.6 meters. So I've significantly increased the length of my dead ends. You can go test this in a lab to verify this. You know, here's a lab test where the jacket failed, and then you actually see that in the field. Here's a picture. We believe this was from a supplier. We believe this was a decoupled design because the cable was from a supplier that uses decoupled designs. But you know, without actually looking at analyzing the cable, couldn't be 100% sure. So to keep moving, what do I think we should use? Well, coupled. And for the US market, we do light only. Again, you have to be cognizant of what the market wants, but I do think that coupled is better. And that's, I've made it clear. Other cable suppliers might disagree with this, but I think if you talk to the people that make the dead ends, they would agree with what I've said here today. So at this point, I want to make an observation about things. So we've seen splice prep considerations not just influence design, but actually be like a driving factor of design in 4 areas: the dry core versus the flooded core, the dry tube versus the flooded tube, the polypropylene material versus PBT for the tubes, and this decoupled versus coupled. And in each case, splice prep consideration has won out at the cost of long-term reliability. And I want to question if that's really what we want. Now, I am okay with the first of these, but I am very troubled by the following 3. I'll concede the first one, not a bad idea, but for the tubes, absolutely, I think flooded is better. I absolutely think PBT is the better material. Again, both of that in the context of ADSS, and I absolutely think you need to have coupling between the strength member and the outer jacket. And I want to give you context on that. So if I'm using flooded tubes, I've added, I said 30 seconds to wipe, 15 seconds to wipe the the gel off the fibers. Let's round it up. Let's just go ahead and go for an extra minute to do that. For polypropylene versus PBT, I don't know that it really changes the time, but we'll see for a minute. Decoupled, again, does it versus coupled, does it change the time? I don't know, but let's just say that we add an hour to splice prep time in total. Really? Splice prep time is on the order of hours already anyway. What's an extra hour? But cable operation is supposed to be on the order of decades. You want this cable to last 20, 25 years, more if you can get it. So why are we concerned about an hour of splice prep time? I don't get it. In my opinion, when there's a conflict between reliability and ease of splice prep, it's reliability that should win when it comes to ADSS. As I say here, the tail should not wag the dog. And I think, I hope that you would agree with me on that point. So just food for thought. So I talked about at the beginning that we would also discuss about what goes into making the tubes and the core. I just want to point out that, as I mentioned earlier, today's manufacturing processes should give consistent, well-coordinated EFL. And to do that, the fabrication process should include continuous inline EFL monitoring and control. And good manufacturers can do that. And in my opinion, you ought to include this requirement in your specifications. The optical core, which is comprised of the tube stranded around your center element, the core should be stranded using a conservative lay length, and that lay length is critical to that zero fiber strain margin that we talked about, and minimizing or eliminating fiber strain at the maximum rated design tension. The core should also be stranded using reverse oscillating lay, and that's where the lay direction reverses every few minutes, because that does help with both midspan access and splice prep in general. So while I may have talked disparagingly about splice techs in this this presentation, I do want to. It's not that I want to make their life harder. As I say here, I'll do something that makes their life easier, but only if it doesn't compromise long-term reliability. So that's where I'm coming from. So last up, what about sag and tension, and what about track-resistant jackets? So basically a very quick primer on both of these. So ADSS, because it's made of dielectric materials, has very different properties than a metallic cable such as OPGW. In a metallic cable, you use your strength to control your sag. In an ADSS cable, you're using your strength to control fiber strain. Because the cable is dielectric, it tends to be stretchy. And stretchy means that you can end up with strain on the fibers. So you want to avoid that. So that's why you use the strength for. With ADSS, you also, because the cable is so stretchy, you have to be concerned about horizontal blowout during wind loading. So the cable can stretch and it can blow out significantly to the side. You've got to check that. And vertical sag has to be checked too. Again, because the cable is stretchy, you don't want to violate your code clearances. Now, some suppliers have gone out and told people, well, you don't really have to worry about that because ice won't accumulate on ADSS. Well, here's some pictures to put to show that that's simply just not true. This is an ADSS cable. It's sagged down to where the man is. You can see it's even touching the ground here, and you can see a tremendous amount of sag on this cable. And it looks like there's a second ADSS here that either didn't accumulate snow and ice or it already shed it. But in any event, one cable still has significant sag as a consequence of snow and ice. So it's simply not true. The industry standard, or the not really a standard, but more like a practice, has been to have 1 to 1.5% of span length sag at every day, meaning no ice, no wind. So if I had 1,000 feet, I would be allowing 10 feet of sag, or 1,000 meters, I would be allowing 10 meters of sag under the everyday condition. So, and then cable suppliers have a design policy on fiber strain. They may not tell you it, but I'm telling you they do. And our practice is, and what I consider best practice when it comes to the sag and tension characteristics of your ADSS, is that it be designed so that there is zero fiber strain up to and including maximum rated design tension. Again, sometimes called MRCL, or maximum rated cable load, but they mean the same thing. That's our policy. And I think that's the best practice. It's not always possible to do this, though. And especially if I'm having to compete against somebody who's not doing this, I might have to do what they do, as long as it's not too crazy. So I do consider acceptable alternatives which have low risk, but it's not zero risk. This basically eliminates risk. These options give you a little bit of risk, calculated risk, or acceptable risk. So you can have zero fiber strain at the nominal, the unloaded, or that everyday tension, but allow some fiber strain at MRDT. So the best is, if you're going to allow strain at MRDT, keep it to 0.2% or below. This number comes from research that Corning did a long time ago, and you can still find their paper where they talk about this. So if you're going to allow strain, keep it to 0.2% or less. Now, you could argue Corning did their research decades ago, and today's fiber is made better, and maybe it can take more strain, and that'd be okay. And I could respect that argument. And if I made that argument, I would say, okay, I might allow 0.3% strain. But you'll find some suppliers that go above this, and they'll allow 0.4% strain. And I don't like that. I consider that to be risky. And I think that anything above that, because we do see some of that from time to time, is just plain crazy. Now, your suppliers, not all suppliers, are going to show you the fiber strain at MRDT, nor will they show you the zero fiber strain margin. But I'm telling you, they have a design policy, they know what it is, and if they don't show it on their data sheet, you merely have to ask. They may give it to you reluctantly, but if you hold your ground, they will give you these numbers, and you can use them to assess the quality of their design. I've given you some good guidelines to go by, and if they stay within that, these guidelines that you see here, and anybody can do it, I'm here to tell you that, if they meet these guidelines, you're going to get a quality product that's going to perform well. And if they don't, you're taking more risk. So check these numbers. To actually get the sag and tension data, most suppliers provide charts. You'll often see them do heavy, medium, and light loading conditions. Maybe you have something special. If you ask them, you can get a chart based upon whatever your loading criteria is. They'll do it for you if you ask. You can also generate your own data using Powerline systems, their PLS CAD program, or Southwire SAG10. For PLS CAD, you need what's called a wire file, which you probably already knew that, sorry. The cable manufacturer should be able to get that to you. Plus, Powerline Systems does have a library of wire files from different suppliers for different cables that's posted on their website. You might find it there too. Of course, the easier thing to do is just ask the manufacturer for it. SAG10, the last time I checked, it was really not suitable for all ADSS cable manufacturers. It was really set up for one supplier that I won't name here. So I don't find their program suitable for general use. We do offer a webinar where we talk about sag and tension in great detail, and on our website we do have sag and tension for ADSS cables, so you can generate your own. And actually, it would actually work with anybody else's cable too. If you fill in the data, it will work for somebody else's cable because it's physics. So I just want to note two things before we keep moving. ADSS sag charts are not temperature related. So you find, if you look at the table, you don't see anything about, 60 degrees F versus 80 degrees F, or changes with degrees in Celsius or whatever. And that's because the cable's got very low thermal coefficient of expansion. And so the standard practice is just to ignore its elongation from temperature alone. But keep in mind, remember, it's dielectric and it's stretchy. So from loading perspective, it's very significant changes in sag for ice and wind loading, but not just temperature change only. And as I mentioned, we offer a tool you can generate your own sag data, for fun and to impress your friends and colleagues that you can do this. So last up, electric field guidelines. So a standard polyethylene jacket, medium density or high density, you want to keep the cable to under 12 kilovolt space potential. The reason for that is that polyethylene will degrade in a strong electric field, and that's going to lead to tracking on the jacket, and the jacket will burn through, and then you're just going to have a cable failure. Everybody has a bad day. So above 12 kV, you need a track resistant jacket. Above that, you're also worried about corona, and so you want to use corona coils. And you do have to be a little bit careful during installation if you're in a high space potential field because of the possibility of induced voltages and current. Of course, ADSS should resist that, but any water or contamination like dirt or pollution could quickly change the cable from being dielectric to being slightly conductive. So you do have to be careful. In general, the maximum space potential for the cable is 25 kV, but you can kind of get around that. There's a way of sort of faking the cable into thinking it's in a lower electric field. And we have a separate webinar where we talk about this in detail. And by the way, you can look on our website. You can find all these webinars. We post the latest recording. So if it's something you want to explore, go do it. So how do you know if the space potential is less than 12 kV or more than 25 kV? Well, here are some general guidelines. So if you're under 35 kV, there's really no danger effectively. From 35 to 138 kV, probably no danger. You have to work hard to install the cable close enough to have an electric field issue, like within inches or centimeters of the phase conductors. But if you're concerned, then the supplier should be able to help you check this and confirm that there's not a problem. From 138 to 200 kV, possible danger, so you should check. And again, the cable supplier should help you. And above, I say here 230 kV, but really above 200 kV, absolutely dangerous. You should use a track resistant jacket and the corona coils, and the supplier can help you verify and confirm the placement details, specifically to confirm that you aren't exceeding the 25 kV point. Now, why do we talk about electric field and space potential? Well, that's covered in detail in that webinar on ADSS and high voltage applications. Just for today, understand that space potential is a more convenient way of analyzing the situation and determining if you are likely to need a track resistant jacket or not. So here's pictures of what actually goes wrong in the field. Corona, you see in this picture on the left, these rods were not installed evenly. And electric fields don't like pointy things. So just this one rod pointing out a little bit has the effect of concentrating the field at this point and then past the corona inception point and allowing corona to form. And then corona quickly burns through any polyethylene material. The way you fix this is to use corona coils. This space potential analysis, to do this, you need to look at the geometry of your line. What you see here is like where the phase conductors of this line are. Here are two shield wires, and you grind the numbers and it tells you what the field is. So the pinkish color means you're 12 to 25 kV. The red color means you're above 25 kV, which means danger. So you could use a track resistant cable. So what you're seeing here is effectively this is where the conductor is. If this is also where the pole is, you would use track resistant in this area. If you're able to stay in the white, like maybe you've got a pole here roughly, if you're able to stay in the white, then you can use a standard jacket. And we offer this analysis software on our website. You're welcome to use it. Oh, so here's actually showing where the actual structure is. So you see again the potential placement points for a track resistant jacket, the potential place for placement points for a standard jacket. And very, just a closing thought, I've already talked about rip cords. They do help, but there's no standard practice for rip cords. So, we think having two under the outer jacket and one under the inner jacket is a good way to go, but ultimately it's really up to you. Anybody can do whatever you want within reason. But you need to specify what you want. A good jacket stripping tool is an option. Here's some pictures of some common ones that are in use today. They're all good. And then, as I just mentioned, ripcord practice varies by manufacturers, so you need to tell them what you want. So, and now we're finished. So, with the presentation part. So, we've got about 10, 15 minutes, or really as much time as you want for questions. So please hit me with whatever you want. You can type it in the chat, or maybe Alexis can let you speak. By the way, thanks to my colleague Alexis, she's acting as like the moderator here, or the facilitator here. Okay, so let me go look at the chat. How can we consider the shrinkage of the loose tube and the amount of EFL we are placing inside the loose tube to establish a limit? Okay, so that question, what I would recommend that you do is that you can specify the amount of EFL in the tube, and a good number to use would be 0.2% for the tube itself. And then you want about 0.25% for the cable as a whole. And that's what you could write into your specifications. That's off the top of my head. I might want to think about that more, but roughly, but yes, you could say that you could specify an amount of EFL in the tube and an overall EFL. And by the way, the truth is you actually need to know the overall EFL of a cable. I'm surprised how many customers never ask about that. Why is that important? Well, because I said at the beginning, the amount of fiber is going to be more than the unit, the length of the fiber is more than the length of the tube. And that also applies to the cable. The length of the fiber in the cable is more than the length of the cable itself. So you actually need to know that when you're shooting the cable. Incoming reception, you get a cable and it shoots, just to pick a number, 6,000 meters. Well, that's 6,000 meters of fiber. What's that mean for the cable itself? Well, you don't know unless you know what the overall EFL is. So actually, you should ask for it. And then the way I would work out what to do with specifications is talk to your different suppliers. So we would give you our numbers. Here's the EFL. Here's our EFL for the tube. Here's the overall cable EFL. And you ask from our competitors, and then you look at the numbers and figure out what you want. If one guy is, if two guys are close to each other and one guy is significantly lower or higher, well, you might want to use the two guys that are their value that is close to each other. And if the third guy is higher, you could say, well, that's okay. But you sort of set the your minimum standard. But if he's lower, then yeah, you throw him out. He needs to either get with the action and do a better job, or get gone. But you're in control at that point. So that's the way I would do it. Is I would ask the suppliers what it is. A variation of that, though, is to just specify the zero fiber strain margin needs to be this, and the allowable strain at MRDT or MRCL, it needs to be this. So that's an indirect way of getting to the same point, and probably a little bit cleaner too. So I hope that answers that question. If not, type more.
Yeah, it did. Thank you.
Okay, great. Can the slide deck be made? Yes. Yeah, I forgot to tell you guys something. So if you want to get credit for continuing education credits, and we're going to give 1.5 hours today, what you do is you're going to get a follow-up email. And the email is going to have a couple links in it. One link is a link to a test. You take the test, you pass with 70%, and you get your credits. The other link is for a survey, and give us feedback. And don't be afraid to throw rocks at me about stuff. I take constructive criticism well. But yes, just respond, tell Alexis, because that's who it's going to go back to, that you'd like to actually see the slides, and she will send them to you. So, oh, and she already wrote that in the chat. Thank you, Alexis. Safety factors used in stress calculations, or MCDT. Okay. Maximum cable design tension. Yeah. Not really, I guess, is the way I would say it. It's how to say this. Maximum rated design tension is based upon the strain of the cable, and what you'll see with most cable designs is that it's roughly 50% of the rated breaking strength. But at least for us, we're trying to hit a certain amount of fiber strain. Maybe some competitors just apply a straight derating factor, like 50%, I said. So if the cable is going to break at 10,000 pounds, they say the MRCL or MRDT is just half of that. So 5,000 pounds or whatever. I think it's a little bit better to actually base it upon a fiber strain limit, but you could do it the other way as well. So if you want to think of that as a safety factor, then that's okay. But other than that, if a cable manufacturer tells you that the MRDT is 5,000 pounds, then you can put 27 inches of ice on the cable and whatever amount of wind, and as long as you keep that tension below 5,000 pounds, you're okay. So you don't need any safety factor beyond the MRDT, I guess is what I'm saying. How do you ensure in your manufacturing process that the fiber strain will not be over the standard limits? If you mean really by standard limits, if you mean your specified limits, well, you're designing based upon those. And the way that you do that is you go make some test cables and go test it and ensure that your designs actually perform the way you've designed them to do. That's what we do, and I believe our competitors do something similar. Nobody specifies fiber proof level, is a factor for allowable strain and reliability. That's actually a good point. This is from Tufik Shanad, and the fiber proof test is basically a standard. Uh, what is the number? 100 kpsi is most common, and so you sort of are working off what the norm is there, and it is possible to get higher proof test fiber, like if you had some real specific need for that, but for a day-to-day purpose, what's commonly done does work, because going back to the question about the safety factor, the fiber suppliers, if you buy 100 kpsi fiber versus 200 kps fiber, you're likely buying the same fiber, but the one fiber has only been tested to 100 kpsi, but it's probably capable of the 200. But the only way to know that is to actually go do some testing of it. So effectively, you are kind of getting a little bit of a safety factor on the fiber. But again, the process that I've outlined here is what's commonly done, and it works. If you have more on that point, I'm open to it, Tufik. What is the usual anti-tracking resistant you consider to be used at the market? So it's not really specified that way, Miguel. I mean, it's interesting question. It's like it's either tracking resistant or it's not.
Yeah, sorry, I meant the US market, not us. Yes, I didn't place it on capitals.
Yeah, I took it as US, but that's a good question. We just rate the jacket based upon the space potential and the field strength, but and we're using the number I used in the presentation, which is 12 kV. And you buy the material and it's capable of that. It's manufactured at it. But in terms of like a resistance as in ohms per milliliter or per millimeter or something, I've never seen it done that way. I don't know why. There ought to be some measure of ohms per presumably either volume or unit length. I have to look at that. I'll pull a cable, the HDPE spec sheet and see if it actually tells you what it is. So anyway, what is the strength considered to establish that a double jacket heavy 180 meter span? Same question for well, there is no single answer for that because it depends upon your loading conditions, how much ice and wind you want to use. So, and then if you tell me, well, I don't want to consider ice or wind, I'm still not going to be able to answer the question with a number. I'd have to actually go run the math. So that's more of an offline type question.
Oh yeah, the question was regarding you mentioned on one of the slides that the recommendation for the span, it was for 180 meters for a heavy double jacket cable. So I wanted to know if you consider a specific strength, because you know that when you increase the sag, you also lower the strength on the cable. However, you also affect how they're going to be installing the cable. So the question was regarding that that specific span that you gave, as well as the condition heavy that you established, it was considering which specific strength on the cable.
Well, it wasn't considering a specific strength on the cable. I think what you're referring to, go back. I think what you're talking about is where I said things like this. this is a rough guideline. And then
Right.
to give context on that, is this slide. So what we're saying is that 600 feet comes from looking at a cable that's really at the 1.5% of span length amount of sag. And you're correct. If you allowed more sag, if you allowed 2%, well, yeah, the cable strength can go down, and the span length could, or you could increase the span length if you change nothing else. But because ADSS is very stretchy, then what you might find under your loading condition is that you have too much sag, whether it's vertical or horizontal, or both. So it's more of a balancing act, I think, than your question implies. There's not really one number. You know, how much, I mean, I could calculate a specific number if I wanted to use NESC heavy loading conditions, exactly 1.5% span. I could give you, well, no, I couldn't, because I still need the cable design. The specific cable design, the fiber count, whether you wanted a single jacket or a double jacket. So it's more of a balancing act. You can see this if you go to our website. We have this ADSS system that helps you pick cables. There's one for OPGW and there's one for ADSS. And if you play around with it, you can get an idea about how these variables interact with each other and lead you to a cable design.
Thank you very much.
Yeah, and other than that, like if you've got a specific case that you're considering, drop us an email and we'll come back with a cable design. So, and then, you know, the strength would be the strength at that point. It would have been designed for that.
Thank you.
How do you consider the thermal modulus to affect the cable and the materials? You really don't, because the thermal coefficient of expansion, as I mentioned, for ADSS is so low that it's generally neglected when it comes to doing sag and tension calculations. Now, a program like PLS CAD, because you do put the number in there, it is going to show, or to take it into account and to therefore show some difference. But in general, with ADSS, you just don't see that. As the span lengths go up, you probably should be checking that, which means if I was doing a very long span, say over 1,500 feet-ish, you know, 500 meters-ish or so, I would probably prefer to use a program like PLS CAD precisely because it would at least check it. But it would still be a lot lower than a metal cable. But beyond that, like the aramid and even the fiberglass, you're not really looking at their thermal modulus. You just want it to be within what you know is going to be the operating range of the cable. And so for most parts of the world, you're looking at like minus 40 C to what, about 50 C plus 50 C. If you're doing a project in Alaska, well, yeah, you might look on the low end more. I mean, I suppose in theory, if I'm doing a project in the Sahara Desert, maybe I would even look on the high end mode, but just to make sure that my material is within the operating range of the environment I'm using it in. But on a day-to-day basis, when you're doing cable design, you're just not looking at the thermal effect on your modulus. Does that help? I hope.
Oh, yeah, it's clear. It's because we have a manufacturer, so I had those kind of questions because we were designing this cable specifically. But yes, thank you very much.
Okay. Which aramid do you recommend? Yeah, there are different grades of aramid, and which you use depends upon the sag and tension properties you're trying to get. So I don't have one answer there. You know, if I'm using like if I'm designing for a relatively short span application, say under 200 feet-ish or so, what's that, around 65-ish meters, and it's a light loading condition, well, I can get away with using like a lower grade of aramid. But back to the other extreme, if I'm doing a 500 meter or a 1500 foot span, then I'm going to be using a higher grade of aramid. So you kind of balance it based upon what you're trying to achieve. And how do you consider the creep each year on the cable related to the lifetime of the cable? Well, you calculate a creep value based upon the material properties, and in turn, there's some implicit assumptions that actually most people are kind of not really aware of that go into calculating that. And what you see on our data sheets, which I could pull one up, but it might take me a minute or two. Hold on. Sorry for the delay. Let me find one. Okay, one moment. Okay, so hopefully you see design details and some specifications. Is that right?
Oh, got it. Yep.
Okay, so this is just the first cable data sheet I found. Hopefully it doesn't have anything wrong or crazy or something on it, and it helps make the point. But anyway, so what we do, and our competitors generally do the same thing too. Not all of them, but generally you calculate an initial modulus and you can calculate a final modulus, and then you do this 10-year with creep modulus. But really, there's an assumption on the creep one about how much load the cable has experienced during that time. So the creep could be a little bit more or a little bit less. If you ask me, well, what is it? And the truth is, I'm going to tell you off the top of my head, I don't remember. We'd have to look at it. But then you go do a creep test and you verify that your cable has met your condition. I guess this calculated value is based upon what the creep test in the standard would be, but the standard is based on just one assumed maximum loading or assumed typical loading of the cable during its life. It could be more or it could be less. But in your question, you had this comment about how do you consider the creep each year on the cable related to the life of the cable? Well, you don't. I consider those to be two separate things. The creep of the cable is going to be whatever it is, and then you're going to then look at the final sag of the cable and the tension too, and decide if that's acceptable for you or not. Right? For your sag, you're looking at maintaining code clearance. And for tension, you're looking at making sure the structure can take it. But generally, it's the initial tension that's more of an issue for the structure design purposes or analysis purposes. And it's the sag that's more of concern when it comes to meeting code requirements. So you have to assess based upon the data that we give you, is that going to work or not? If you think your loading might be higher, then you might question this value and maybe we could talk about it and calculate a new one. and then go test it to verify it, because that question has come up before here too. How do you know that these things are correct? Well, some of it is simple math. Your cable diameter, that's pretty easy one to check. But things like modulus and tension and strain margin and things like that, you have to actually go to the bat cave, so to speak, and go actually do tests to verify that your design model is giving results that are accurate. And, we do that, and I believe, well, I know good competitors do that too. So, does that answer your question? Good enough?
Yeah, it's good enough. Thank you very much for answering all of my questions, because I made a lot of them. But yeah, thank you very much. We also are trying to get in the IEEE, the IEE standard. So yeah, that's why I made all those questions. But thank you very much.
And
Very
what do you
grateful.
mean? Yeah, you're welcome. What do you mean you're getting into the IEEE standard? You mean you're like
Oh,
reading it?
no, or we're getting our cable to test it that way on the IEEE standard. That it's for the ADSS cables. It's from Telcordia year 20, and it's gonna tell you to look into that standard, and that standard is gonna ask you for so many things, and that test it's like really hard to do because of the how you measure the MRCL, the maximum rated cable load, and all that information. So I think that could help me a lot to finish the development of the product.
Okay. Well, to do the testing, some testing even we go to an outside lab for. We do some internal testing, but some things you go outside, if that
Right.
helps.
Thank you very
Okay.
much, Mike.
Yeah, you're welcome. You're welcome. And then I have the question, how is the lay length related to the fiber strain? And how do you define it? Well, the lay length, sorry, now I need to go back to, hold on. Where was that puppy? Bear with me for a moment. Lay length, here we go. So the lay length is the distance it takes an element to make a complete circumference around whatever the tube or a wire or strand of aramid, whatever it is, whatever it's being stranded around. That's your lay length. And yeah, I mean that's a factor in your overall cable EFL. You end up with a helix here, and that helix is effectively increasing the amount of EFL in the cable. And it's a balancing act for, in general, to, how to say this? I said, in general, EFL, you want higher the better. But in the real world, there are trade-offs. You can understand that if I make the lay length really short, if I made a 1 millimeter lay length, I end up with something that's more like a spring than a cable. On the other hand, if I make the lay length 27 meters, I end up with a tube that's effectively straight, as if it's not stranded. So the balance, you have to find a balance between the lay length being too short of a lay length, like what kind of problems is it going to cause? Well, mechanically, it's going to make a cable more stretchy because it's going to be effectively more like a spring, in particular, a metal cable. It's also kind of going to get jammed up at very low temperatures. And then on the other end, if I make the lay length too long, what happens is I don't have enough, or the cable under tension, I end up with lower effective EFL, and so the cable under tension has a lower zero fiber strain margin, which in turn means I get more strain on the fibers when the cable's under tension. So too low of a lay length tends to kind of compromise low temperature performance, and too long of a length tends to compromise general tension performance. So you got to find that balance in between. So I hope I've answered the question. Do your ADSS cable designs comply with? Yeah, we do. And the IEC ones too, when we're selling outside the United States. So, but like when you're working with any kind of an aerial cable, there are a couple of basic things that the cable needs to do right off the bat. It's kind of like if you're playing poker and you got to put an ante into the pot, so to speak. And one of those basic things is tensile performance. You know, if you design a cable and you say it can hold 10,000 pounds, well, then that's a basic thing. You need to be able to do, absolutely, you need to be able to do that. So hope that answers that question. Anything else? Okay. I appreciate everybody's time and attention today. I especially like the dialogue after the fact. Some of the questions are a little bit tough, but that's okay. I like that. Makes things more interesting. Thanks again for your time and attention. You're welcome to reach out, follow up with us. You'll get, respond to the follow-up email, and you can get my email if you have more detailed questions or more specific issues that you want to talk about. Happy to help out with that. So thanks again. We're done for today. Enjoy the rest of your day.